Hi guys, let's continue our look at substitution reactions, and we'll pick up here with section E, reactivity of various electrophiles in the SN2 reaction. As we move along here for the next lecture or two, we'll focus on SN2 reactions. We introduced them both early on, both SN1 and SN2. But we'll focus on SN2 reaction for a while, and we'll look at both components of the reaction, the nucleophile as well as the compound with the leaving group. And the compound with the leaving group is the electrophile because it reacts with the nucleophile. So let's look at reactivity of various electrophiles and make a few different comments. And the first will be the effect of a p orbital being immediately adjacent to the reaction site. Now if you look at these four compounds here, and in each case the leaving group is a chlorine, so that's consistent. Now all four of these are going to be more reactive towards a nucleophile, that is towards a nucleophile coming in here and displacing this chlorine leaving group. These four are going to be more reactive than this molecule here. And the reason is because adjacent to the reaction site, in each case, there is a p orbital. We can draw that here. We see the pi bond there. There's p orbitals on each atom in this ring. There's a p orbital here, and one there, overlapping, make that pi bond. There's a p orbital here, and on the oxygen, overlapping to make that pi bond. And there is one here. Now there's actually two on that carbon because that carbon is making two pi bonds to the nitrogen. But we only need one. Now this molecule is going to be less reactive because there's no p orbital adjacent to the reaction site. Now, why does the p orbital adjacent to the reaction site make these more reactive? So we have a nucleophile, it's going to have a lone pair, may or may not have a charge. This comes in, kicks that off. Okay, we're focusing on SN2, so it's a concerted backside attack, kicking off the leaving group. But remember what we said in the last video. In this transition state, alright, it becomes trigonal planar with sp2-like character. Now it looks like I didn't draw this in last time, but trigonal planar with a p orbital. This now looks like a traditional sp2 hybridized carbon. And this bond formation and breaking sort of kind of is in this p orbital type arrangement. But down here, when this p orbital arrangement is formed in the transition state, okay, it can overlap with the adjacent p orbital. For example, if we drew one here, okay, if there was a p orbital next door up here, in this transition state, as this sort of becomes like a p orbital, we can get overlap here. And this p orbital overlap would stabilize the transition state. And that can occur in all four of these molecules. But it cannot occur in this molecule here because there's no p orbital next door. And so this molecule would be less reactive. The transition state would not be stabilized. It would not be as lower in energy as it would be for these molecules above. Actually, these four here they tend to be toxic. That's because they react easily with nucleophiles in vivo. And that just means in the body. Okay? But these tend to be very reactive. You have nucleophiles in your body, such as in proteins. You have amino groups in proteins or DNA, and those groups can act as nucleophiles. Okay, number two. We can look at the effect of carbon substitution at the site of nucleophilic attack on the reaction rate. Now, methyl bromide is very reactive in an SN2 reaction and thus toxic. And it's more reactive than a primary halide. Here the halide is on a primary carbon. And that's more reactive than a secondary halide. And that is much more reactive than a tertiary halide. Now the reason here is because of steric crowding, or steric hindrance. If we look at a carbon with a leaving group, now in this case I'm showing bromine as a leaving group, all right, but I'm keeping it consistent. If we have H's here, those H's are small. Now it's also tetrahedral. And I didn't draw the tetrahedral nature, maybe I should have, but a nucleophile is going to be able to get in here and kick that leaving group off. Very easily. But if we go to the other extreme, if those are methyl groups on that carbon, 3 methyl groups, well, you got to keep in mind that those methyl groups also, the carbons also have H's. And if we draw these H's in, you'll see that it gets fairly crowded. And crowding we call sterics. Steric crowding, and it's a hindrance to the reaction, so we call it steric hindrance. But here, if a nucleophile is trying to get backside to that carbon to kick off the leaving group, it's like, I can't, how do you get in there? And it doesn't. And we end up with no reaction because of steric hindrance. substantial steric hindrance. Now this is a tertiary halide. The halide is on tertiary carbon. And we can make a statement here in bold. Never do SN2 with a tertiary halide. Okay? We would say that it's too sterically hindered. So we're going to cut it off right there. You can do SN2 on a secondary halide. It's not going to be as reactive. The rate will not be as good as if you were reacting with a primary halide, but you still can do SN2s with a secondary halide. But in this class, we will never do an SN2 with a tertiary halide. Now this also applies to other leaving groups. Okay? Now I'm going to write this down, but it really doesn't need to be stated. Basically, what we mean here is LG. Okay? As we move along, we'll see there's other leaving groups other than halides. So, again, the effect of carbon substitution at the site of nucleophilic attack. As we move along here, we get more carbon substitution at the carbon which contains the leaving group. And never do SN2 with tertiary halide. The rate is just too slow. This table here shows some examples of that. We have an alkyl bromide. We're reacting it with lithium iodide. So the nucleophile here is I-. This is essentially replacing one halogen with another. The iodine is the nucleophile here, iodide. Acetone is solvent. Now we have an alkyl iodide, and we produced lithium bromide as the byproduct here, a substitution reaction. If the R group is methyl, the rate is 163. If it's ethyl, so we have the carbon that's being attacked has an additional carbon substitution, the rate decreases down to 1. If we add another group to the carbon, the rate decreases substantially further. If we have 3 groups on that carbon, it becomes negligible. And at this point, we would say no reaction. But you do see it's rather slow here compared to the others with the secondary, but here is sort of going to be our cutoff. That's some exact data there for a SN2 reaction. A trip to the dentist. The idea of steric hindrance is seen throughout organic chemistry. And for those of you who maybe are pre-dental, if you look at the local anesthetics that are used in dentistry, you will see that some are short-acting, some are moderate-acting in length, and some are long-acting. And that is largely based on how fast the anesthetic is hydrolyzed in the body, or metabolized by hydrolysis. And the metabolism is largely based on steric crowding. And the more sterically hindered the amide group is, the carbonyl group of these anesthetics, the slower the metabolism. And thus it turns out that the more sterically hindered anesthetics are the ones that act the longest. Again, because it slows down the metabolism. Sterics slows down the reaction because of crowding. And with crowding, the groups just can't come together as readily the way they need to in the mechanism. And thus that reaction, we can go back and refer to this K factor in the rate equation. Okay, the concentration can be the same. The concentration for these reactions are indeed the same whenever you do rate comparisons. So if the concentrations are the same, what changes the rate? Well, it's sterics. And when you look at the rate equation, that's sterics is built into this K, this constant for a given reaction. There are, of course, other things built into K, but sterics is one thing that is. Okay. In terms of these anesthetics, if you want to compare these, look at lidocaine versus etidocaine. You can find these on Wikipedia. And you'll see that the carbonyl group of etidocaine is more sterically hindered or congested with other groups. Okay, let's look at the leaving group ability. Over here I kept the leaving group the same because we wanted to focus on the carbon next door. But what if we change the leaving group and keep everything else the same? Well, as we mentioned early on, the leaving group ability of the hydrogens is as follows. Iodine is a better leaving group than bromine, which is a better leaving group than chlorine, which is a much better leaving group than fluorine. So the cutoff is sort of right here. This is largely due or based on the stability of the resulting anions. When these serve as leaving groups, they're going to leave as the anion. In previous reactions, we showed hydroxide displacing the bromine, and it left and it became bromide, the anion. Well, which is the most stable anion? I minus. And that's more stable than Br minus. And that's more stable than Cl minus. And of course, Cl minus is more stable than F minus. But the leaving group trend is largely based on this. By the way, I minus, if you remember, is more stable because it's larger, and the negative charge is dispersed over a larger volume here. So if you react these two alkyl halides with methoxide, okay, this is O-methyl minus. That would be called methoxide. If that was a hydrogen, it would be hydroxide. All right. And we're doing an SN2, so this comes in and displaces the leaving group. And now the O-methyl is bonded to the carbon. Two lone pairs. The other lone pair is now bonded to the carbon, as shown in our mechanism. And we produced I minus And the potassium is just a spectator ion. It was over here. K plus was over here. It's over here as well. Okay. Same reaction below, but down here we would produce F minus. Okay. But I minus is much more stable. Thus, it's willing to serve as a leaving group much more readily than F minus. Trying to displace the F minus, you call it F here, but it becomes F minus, much more difficult to impossible. Okay? So ultimately, we would say for this class that this reaction will not occur, but the one above will. The transition state here is just too high. All right. We can say that the F minus is a poor leaving group. I will actually say very poor. Now, can other groups be leaving groups? And their answer is yes. Oxygen. Oxygen can be a leaving group for SN2 reactions or SN1. But we have to sort of activate it, make it a better leaving group. And the first way is going to be by protonating it. Okay? Now, if we try to do the same reaction above with methoxide, and maybe, okay, these electrons, we say, hey, we're going to come in here and kick off the OH group. Well, that's not going to happen. A regular OH group will not act as a leaving group in a slow rate determining step. Okay? Now you got to make sure you understand what this is in a slow rate determining step. I'll just go ahead and note here. It can leave in a fast step. All right. Now I don't want to confuse things here, but at the same time we need to understand rate determining steps for our two mechanisms. All right. And if you look at our two mechanisms as a review, I could ask a question. In which mechanism does the leaving group leave in the rate determining step? For SN1, rate determining step is leaving group leaving. Ionization of leaving group leaving. For SN2, what's the rate determining step? Well, there's only one step, and the leaving group has to leave in that one step. The leaving group leaves in the rate determining step in both mechanisms. Hopefully you remembered that. All right. So this statement applies to both SN1 and SN2. In organic 2, we will see mechanisms in which the leaving group leaves in the fast step. I'll just make that note. But when we get to organic 2 and we talk about this, you guys will say, no, OH is a bad leaving group. And I'll have to remind you, yes, it's a bad leaving group when it leaves in a slow rate determining step. That's the hard step. okay? Or I'll call it the difficult step. Okay, just a little bit extra commentary there. Just make sure you understand your rate determining steps for each mechanism. Now, look at this reaction. If we take the same alcohol with the OH group and react it with methanol, not methoxide, but methanol, the neutral version here, but an acid catalyst, I'm going to say catalyst, we can get a substitution reaction. And we can replace the OH with the OMe. All right? Now this oxygen is different. We didn't just add a methyl group to this oxygen. We have replaced it. If we star that oxygen, this oxygen over here is now starred. And the mechanism here involves first protonating the OH group, or the oxygen. Acid-base reaction. Standard acid-base reaction to protonate the OH group. Now we're using a strong acid, okay? We'll come back and mention a little bit more about this. Now, this is a good leaving group. The positive oxygen. And now the methanol will act as a nucleophile, okay? All we need is a lone pair. It doesn't need to be a minus charge. Okay, up here we were using the anion. Here we're using neutral, and we'll talk about why. It has to be neutral. The electrons attack here, and bam, kick off the leaving group. And that will give, not that product yet, 3 carbons. Now attached to this carbon, I'm going to draw it zigzag up. It doesn't matter. We have free rotation. Oxygen here, but the oxygen has a methyl and an H, and 1 lone pair left. That oxygen now is positive. But what was the leaving group here? What actually left? And the answer is water. H2O, 1 lone pair. This arrow gives it, the oxygen, its second lone pair back. And there's water. I'm not going to redraw that here. But H2O is the leaving group here. Now, to get to our final product as shown, we need to remove the proton. We've done this before, like when we hydrated an alkene with water, we had to remove a proton. Same thing there. There's got to be a minus. I didn't show anything. We could use water. The water that was formed, something needs to take it. These electrons take the H, these stay behind. And we would form H3O plus. Or Depends on what we used here. If we use sulfuric acid, there would be a bisulfate anion. We could have taken the H there, and we would have reformed H2SO4. See, I like to do that because then we see, okay, I reformed my acid, and I didn't sort of convolute what happened to the water. The water was also formed. All right, that was new. But then the acid was reformed by the anion taking this H, and we reformed the catalyst. So a lot of similarities to when we were doing alkene reactions, dealing with that proton. But here the water is the leaving group. It will leave because when the oxygen leaves, it becomes neutral. So positive oxygen will leave, where up here a neutral oxygen will not, because if a neutral oxygen leaves, it has to become an anion, and an oxygen anion is much less stable than any of these halide anions, and it turns out that it just will not leave in a rate determining step. Okay. Why did we use the neutral nucleophile? All right. Why not use an H plus catalyst and the anion? Well, that's because these are not compatible. You cannot have a strong base and a strong acid in the same reaction. Okay? Potassium methoxide is just as basic as potassium hydroxide. KOH you know is a base. Hopefully you know that KOMe is just as basic. It's an oxygen anion. Bases cannot exist with acids. They're just going to neutralize each other and there will be no additional chemistry. All right. But let's point out this reaction. This is a common reaction of alcohols. Reaction with HX. Now this is H plus I minus. You can have halide anions with acid. That's the definition of a strong acid. It's acid and then the conjugate base. And in this case, the acid serves to protonate the alcohol, and then the I minus comes in here and kicks off the water, and there you go. We can get the alkyl iodide and water leaving group, and that will work. So these two are compatible. And they come from the same molecule. The HI supplies both the acid and the nucleophile. Where in this example, the acid came from some type of added strong acid such as sulfuric, and then we had to have the methanol as a second molecule which acted as the nucleophile. Remember, just like with alkene reactions, bisulfate will never act as a nucleophile, at least not in this class. So Conversion of alcohols to alkyl halides using HX is a very common reaction. By the way, the H plus here is not a catalyst. Because it's not reformed. We never remade H plus, nor did we have to. And so by definition, it's not a catalyst. But you got to be careful. It's still needed for the reaction to take place. So you might call it a promoter, but you wouldn't want to call it a catalyst. Because if you got to have H plus here. If you just tried to take the alcohol and react it with like sodium iodide, there would be no reaction. Because if you tried to get just I minus to come in here and kick that off, it would not happen. Because what do we know about OH? Have a very poor leaving group there. Okay? Just like here. Methoxide's not going to kick it off. No nucleophile. Okay? No reaction with any nucleophile. So instead of sodium iodide, we need HI. Or, go ahead and show this here. We can say H plus needed. We could get the H plus from using HI, or you could use sodium iodide and maybe sulfuric acid. Aha! The sulfuric acid would supply the H plus, and the I minus would come from the sodium iodide. And that would work. Okay. In addition to OH groups, OR groups can also leave if the oxygen is made positive by protonation. Okay? Doesn't have to be OH, it could be O carbon. All right? Predict the product of this reaction here. What type of substitution product could you envision or predict here? We'll look at that in class. Okay, B. What is B? What was A? Making oxygen a good leaving group. The first way is by protonating it. Protonating it, we make it positive, and it will then be a leaving group. The next way to make OH a better leaving group is by converting it to a tosylate, or mesylate, or triflate. These are called pseudohalogens. They're not halogens, but they act as if they are. A tosylate is shown here. The oxygen is bonded to a sulfonyl group, then to a benzene ring and methyl. Benzene with methyl is called toluene. It's sometimes used in lab, the Diels-Alder lab. Toluene connected to the sulfonyl is called toluene sulfonyl. And if we shorten that, we can get tosyl. And with the oxygen here as an anion, it's called tosylate. Okay. Now tosyl is abbreviated Well, that's tosyl. Okay, this is called tosyl. If we have the O there, it would be called O-tosyl. Now, O-tosyl is abbreviated OTOS or O just TS. Now, most textbooks actually just say TS. I like to put in the TOS so we can pronounce it OTOS. Now, this will serve as a leaving group. And a nucleophile will come in here and kick this oxygen off. And that will give our nucleophile now bonded to our carbon. And the leaving group became oxygen, now there's 2 lone pairs here. The oxygen should now have 3 lone pairs. Third lone pair coming from this arrow movement here. That oxygen is now a minus. And here is your tosylate anion. Which was our Lg. Now, why will the tosylate anion serve as a leaving group, but the hydroxide ion will not? Okay, the hydroxide will not act as a leaving group in a rate determining step. Why will the tosylate be a leaving group? And it's because it's stabilized. It is a resonance stabilized tosylate anion. We can draw resonance. I'm not going to draw full resonance structures, but electrons in, electrons up. This oxygen, this anion can be delocalized onto that oxygen, but also onto the other oxygen as well. And so the tosylate group will serve as a leaving group without having to protonate the oxygen. It'll serve as a leaving group just like a halogen. That's why it's called a pseudohalogen. You do not have to protonate it. Now there's variations of the tosylate. You have the mesylate. That's where instead of a toluene group bonded to the sulfonyl, it's just a methyl, and thus it's methyl sulfonylate, shortened to mesylate. If it's a trifluoromethyl, it's called a triflate. These two may not be shown in your textbook. These are a little bit more advanced, but it's the same idea. Okay, nucleophile attacks here, kicks that off, and the triflate can serve as a leaving group. There's a couple others to show. These are kind of like variations. The diesters of sulfuric acid. Okay. If these methyl groups were H's, that would be sulfuric acid. If we make them methyl groups, now we have a carbon bonded to an oxygen that's bonded to these sulfonyl. And a nucleophile will come in and kick that off. Same thing here. Now this is an ethyl group. Kick that off. This is called dimethyl sulfate. This is called diethyl sulfate. These are very cheap, and these are common, we can use this term here, common alkylating agents. Because the nucleophile is going to become bonded to the methyl. That's actually a methylating reagent. Here the nucleophile becomes bonded to an ethyl. This would be an ethylating reagent. But in general we can call these, and really anything with a great leaving group, okay, an alkylating agent. These are very potent alkylating agents because a nucleophile will react here, and you're going to then have an alkyl group bonded to your nucleophile. The saturated carbon would be called alkyl. Of course, the ring is an aryl. Okay, how do you make tosylates? Tosylates are made from OHs, okay, by reacting with tosyl chloride. Tosyl chloride would be Cl SO2, and then the toluene group. I'll just abbreviate that with sort of the Greek symbol phi, which is often used to denote an aromatic. That's tosyl, basically tosyl, and then a chlorine under my finger. Okay. And the alcohol will displace the chlorine. Pyridine is benzene ring with one nitrogen, has a lone pair. It's used as a weak base. And it's a substitution reaction itself. The oxygen displaces the chlorine off of the sulfur, and then we generate HCl, but the pyridine reacts with the HCl. We'll look at this reaction mechanism in Organic 2 when we revisit tosylates. Important at this point is whenever you make a tosylate, the stereochemistry at the carbon does not change because we're just reacting the oxygen with the sulfur. There's no chemistry taking place at the carbon. Now we have a good leaving group in the tosylate. Now if we do a reaction, now we're doing chemistry at the carbon, backside attack, kick off the tosylate, SN2, and we would expect inversion. Leaving group forward, and so the nucleophile came in from the back. Okay, so there's oxygen. We can make it a better leaving group by protonating it, making it a positive, or with OH groups, we can convert the OH to a tosylate, which acts as a pseudohalogen. You do not need to protonate it, and we can then do an SN2. When we make the tosylate, there's no change in stereochemistry at a chiral carbon that the OH is bonded to. But of course, if we then do an SN2, we're doing chemistry at carbon, and we would expect a SN2 inversion. I don't think I've said it yet, but SN2 comes with inversion like Big Mac comes with fries. What about other atoms? Can a nitrogen be a leaving group? And the answer is yes. As with oxygen, though, Nitrogen can only be a good leaving group if it's given a positive charge. Okay? We have to give the nitrogen a positive charge to make it a good leaving group. Now this is not as common as oxygen, but it's still possible. If you look at this reaction here, why don't you do the mechanism of this on your own? Think about that. We're reacting with HI. Here are your products. Show mechanism for that. All right, it is an example of a nitrogen serving as a leaving group. It's not that common, but it is possible. Your most common leaving groups are your halogens and oxygen. But with oxygen, we have to activate it somehow. What about other atoms? Well, there's one more I want to point out, and that's sulfur. Sulfur can be a leaving group sometimes, but just like oxygen, typically it needs to be made positive first. Now your body actually uses sulfur as a leaving group when it makes epinephrine. And norepinephrine has an amino group which acts as a nucleophile. And it actually will attack the methyl group. This is kind of small, and that's a positive sulfur, if you can see that on your handout. That positive sulfur will leave, and the nitrogen becomes bonded to the methyl, shown here. Now the nitrogen does need to lose an H. Something will take the H and give the lone pair back to nitrogen. I'm not going to show full mechanism here. There's got to be a minus here. But the SAM, got it. S-adenosylmethionine is a biochemical compound which actually serves as a methylating agent in the body. But a positive sulfur is the leaving group, okay, for an SN2 reaction. Application of this, mustard gases. This molecule here is called a sulfur mustard gas. It was used in chemical warfare in World War I. Very reactive and thus very toxic and quite dangerous. What happens here, this molecule, these electrons will react internally and do an internal SN2. On either side, it's the same, symmetrical. And now the sulfur is bonded there. One lone pair left, positive charge, plus Cl minus. And this will take place sort of spontaneously, driven by entropy, one molecule breaking into two different species. But look at this. Look at one of these carbons now. They're symmetrical, they're the same, but now a nucleophile will attack this carbon and kick off the positive sulfur. But this is very reactive for two reasons. First off, a positive sulfur is a good leaving group. It would love to leave and go back to neutral, get its lone pair back. But another reason that makes this very reactive is you have a ring here, ring strain. And the nucleophile coming in here and opening this back up is very easy because it relieves this ring strain. All right. You may ask, well, why did this happen in the first place? Why did it make this ring? Strain ring. Well, driven by entropy. Entropy is a very major driving factor. But it leads to something that is very reactive. And then nucleophiles in your body start reacting here. Now these nucleophiles are going to have an H, like this here. Norepinephrine could react. Okay? But then the nitrogen will need to lose an H. And ultimately the Cl minus can take it and you're going to start making HCl. But making HCl in your lungs is going to be bad news. So, a little bit of trying to understand here the chemistry of sulfur gases. Mustard gases. They're called mustard gases because they're yellow. You do not want to breathe these in. Now, some of these can also be used to treat cancer. Alkylating agent. This is a nitrogen mustard. This lone pair attacks here. Okay, and we get the I'll just draw these like this, positive, and then some nucleophile can come in here and kick off the positive nitrogen. But these are some older drugs used to treat cancer as alkylating agents, and alkylation of the cell DNA is going to maybe ultimately kill the cells and could kill the cancer cells. The problem with these are they're not that selective. They would end up harming the good cells in addition to harming the cancer cells. But this is sort of the mechanism for how they would work. Okay. So we see sulfur, positive sulfur leaving, positive nitrogen leaving, and these sulfur mustards, or nitrogen mustards, they're called. I see we had it showed here. Yes. Okay. Next we'll move to start talking about the nucleophile. Okay. So go back over here. We just talked a good bit about the compound with the leaving group. Next we'll move and start talking about different nucleophiles. And how changing the nucleophile can change the rate of the reaction, the ease or difficulty of the reaction. Okay, I think we'll end here. That's a good place to end. Okay, guys, till next time.